Right, in chapter 4, we talk about motion in 2 dimensions. And up until now, we've been talking about motion in a line, or one-dimensional motion. And everything's been acting on that particle or car or whatever it is in a line. Now we're going to worry about 2 dimensions at the same time, x and y, for example. The first case we're going to look at is something called projectile motion. This is a very specific case of motion, but it comes up a lot, especially a lot in physics. A projectile is considered anything that once it leaves, like I'm going to throw this tennis ball, once it leaves your hand, there's no force acting on it except gravity. Then it's what's considered a projectile. Okay, so in this case, I throw the tennis ball. Once it left my hand, I gave it an initial velocity. All of the rest of it was determined by the acceleration of gravity. And so that's what we consider projectile motion. So what that means is there's no acceleration in the x direction. And in the y direction, acceleration is equal to g, but it's going to be negative because we're going to keep down being negative value everywhere. But remember, gravity is a constant. It's just 9.8 or 9.81 meters per second squared. So we can use our constant acceleration equations. So you remember these. Hopefully you should get these memorized by now because we use them all the time. In fact, you will use them throughout the whole semester. One thing about physics is it builds on everything. Everything you do builds on something before. So remember, these were the equations. There were 3 equations. We have x is equal to x naught plus v naught t plus 1/2 at squared. V is equal to v naught plus at, and v squared equals v naught squared plus 2a x minus x naught. Those were our constant acceleration equations. So we're going to rearrange these equations, or we're going to put these equations specifically for projectile motion. Now, in the x direction, so we're going to do x direction first. Let me do it in a different color here. Sorry. In the x direction, we say, okay, we have the first equation, but acceleration is 0, so that term goes away. So what this becomes is x is equal to x naught plus v naught x. Now we have to put an x under here, so this is the initial velocity in the x direction specifically, times t. Or this becomes our original equation, the very first equation we learned. Remember, this is distance, and if x naught is 0, this is distance is equal to velocity times time, which was the first one we ever learned for a constant speed. That's the case in the x direction. There's no acceleration in that direction. Remember, we're ignoring friction. And if you look at the second one, the velocity, this is going to be 0. The acceleration is, so the velocity is just equal to the velocity in the x direction is just equal to the initial velocity in the x direction. There's no function of time here because it's constant speed, so nothing will ever change. So that's all you have in the x direction. If you do this one, notice here that the acceleration is 0 and v squared equals v naught squared. Well, you take the square root of both sides and you get the same exact equation. All right, let's look in the y direction. In the y direction, things change a lot. So we're going to do the first one, but we're going to replace x's with y's. So y is equal to y naught plus v naught y. Remember, we have to do just the component in the y direction, times t. This is going to be minus, because we're replacing a with negative g, so this is minus 1/2 gt squared. So that's that same equation. We've just replaced it with y's, and we've put a negative in because we're always going to make down be negative. Just got to be consistent on that. And then we have the velocity in the y direction is v naught y minus gt, because our acceleration becomes negative g. And then the last one becomes vy squared equal to v naught y squared minus 2g y minus y naught. All right, so those are the constant acceleration equations now specifically for projectile motion. Now there's a couple of other things we have to look at for projectile motion. For example, let's say I have a cannon that's launching a projectile here. It's going to launch it with initial velocity v0. And it's going to launch it at an angle theta. Alright, so what we have then is v naught, but what we want in these equations, we want v naught x and v naught y. So we have to use our components that we learned in chapter 3. So we're going to split v naught into two components. One component here we're going to call v naught x. One component this way we're going to call v naught y. And then using our trig equations, we realize that, oh, v naught x is equal to v naught cosine theta. And v naught y is equal to v naught sine theta. Okay? A couple more things that we can use to our advantage when we have projectile motion. I'm going to extend this out here. We know that when the object is launched, it actually follows a parabolic shape. And that parabolic shape has a point right here at the highest point. When you reach the highest point, what do we know? Well, at that point, the velocity in the y direction is equal to 0. It's like throwing the tennis ball straight up. There's this brief moment there where it stops, and then the velocity changes direction and it comes back down again. We can take advantage of that when we plug that into our equations. If we're trying to figure out at the top, and we know the initial velocity, and we know vy at the top is 0, and we know the initial velocity, we can solve for what time it gets to the peak of its arc. And so you can take advantage of that fact up there. It doesn't work for the x direction because that velocity never changes. Yeah? Now we also can calculate something called the range. And so we can have the range, and the range is the distance a projectile goes, but you can only use this equation if the launch and landing are at the same height. If they're at the same height, then we can take advantage of that. And we can take advantage of the fact that the same height means that y will be equal to y naught. So this is going to be 0 here. This is going to cancel each other out. And we can actually solve this for t. We can plug it back into here, and we can get an equation to get the distance. And what you get is that the range is equal to v naught squared over g times sine of 2 theta. All right, this is the specific range equation. That tells how far it goes in the x direction, but that only works again if it launches and lands at the same height. If you're up here on the top of a cliff and you throw it down, you can't use this equation. Or vice versa, if you're throwing it up to the top of a hill or something, you can't use that equation. They have to land at the same height. Notice what this tells us, though, is that the initial velocity squared divided by g, right? This doesn't have any components. This is the initial velocity. It's not v0x or v0y. It's just v0 divided by g, and then the sine of the angle. So if you think about, well, what would give us the maximum range? Well, the maximum range occurs where you get this term to be the biggest. Remember, the sine or cosine or all of the trig function, sine and cosine can never be bigger. Yeah, don't do the other ones. But sine and cosine can never be bigger than 1. So the biggest that could ever be is 1. And that occurs when the sine is equal to 90 degrees. But here it's 2 theta, So we have to have what's 2 times what gives you 90 degrees, what's 45 degrees. So you get maximum range at a 45-degree launch angle. All right, now, most of the time, you might say when you watch sports or something like that, and you watch golfers trying to hit it as far as they can using their driver, they don't launch it at 45 degrees. That would be very, very high. They launch it at about 15 to 20 degrees. But the difference there is we are ignoring air friction. They have to deal with air friction, and they spin the ball backwards, and that holds it up in the air for a long through time. And so that changes the range equation completely. Baseball's closer to this, especially for like home run hitters. What happens with a home run hitter is when the pitch comes down, because the pitcher's on a mound, the pitch actually comes at a lower angle. Home run hitters tend to swing slightly up, and so if they connect on it just right, the angle coming down or angle coming up will put it at close to 40 degrees, which gets them maximum distance. The ball comes off with a little bit of backspin, which accounts for that extra about 5 degrees. And big home run hitters that hit a lot of home runs just naturally tend to hit it at that angle. If you hit it lower than that, you don't get the maximum range on it. All right. There is one other equation, because you see that this actually forms a parabola. And so what I can do is I can solve this for t. Actually, this for t here. Change this, solve this for this, plug this back in this, actually solve this for t, solve this for that, put that back in there, solve all this, and you're like, what is he talking about? You can get one more equation where you eliminate t, and you get y in terms of x. And when you do that, you get this.